Hi everyone, this is Jim Corkins, and this recording is going to be for Physics 101, Physics 111, and Physics 121. If you haven't had the chance, please start doing the reading in Rotational Motions, the Rotational Motion chapter of whatever book that you have, whether it's OpenStax, Coletta, or Knight. Okay. And so what we're going to begin with is the introduction to rotational motion. Okay? So over the entire content of rotational motion, we're going to cover polar coordinates, centripetal acceleration, angular velocity, angular acceleration, torque, center of mass, moment of inertia, angular momentum, and rotational kinetic energy. And we're not going to be doing it in those orders, but we are going to be covering those topics. Okay. So let's begin with just the basics of circular motion. So circular motion is characterized by two different types of motion: tangential or linear speed, and this is the type of speed that we've already been doing this entire time. Objects falling, objects moving in the x direction, moving in the x direction, with a velocity in the x direction. You got a little ball moving in that direction, so it's moving in the positive x direction. Or suppose you had another ball falling to the ground, okay, and it's got a negative velocity in the y direction, okay. The other type of motion that is part of circular motion is rotational motion, okay? And specifically, you've got rotational displacement, a rotational speed, and also rotational acceleration, okay? So we're going to be attending to all of those things right here in this first presentation. It all begins with this. Suppose you had a wheel that is it's got a radius of 1 meter and it's rolling across the floor at a constant velocity. And it makes one full revolution as it's rolling across the floor. Could you just take a moment to tell me how many degrees does it roll through in this one revolution? How many radians or how many pi's does it roll through? And pi, the number, 3.14, does it roll through, which is related to the number of degrees. And then thinking about it, how far would it actually roll if it rolled one full revolution and had a radius of 1 meter? How far would it have rolled in the x direction? Okay, and so you have the wheel right here, and it's going to be rolling, it looks like clockwise. So how far is it going to roll? So pause the video and think about this and try to come up with numbers for the degrees, the radians, and how far it would actually roll in the x direction. Please pause now. All right, so we've got this wheel that's 1 meter in radius. So that means essentially that this little guy right here is going to be 1 meter in radius. Right there. So I'm just drawing on the little wheel there, the radius. And it's going to make one full revolution as it's rolling. So this wheel is rolling clockwise. So that means it's essentially going to be rolling, and let's just say it takes 0, 1, 2, 3, 4. It takes 4 seconds to do it. So it starts at 0 seconds, and then 1 second, 2 seconds, 3 seconds, and then 4 seconds to roll this one full revolution. So it's going to be rolling to the right, okay? And so one revolution, well, how many degrees would something roll through if it started at the top here and then rolled a revolution, and then this dot that was at the top is now at the top again? Well, it would have had to roll through, well, this is going to be from 0 seconds to 1 second, that's 90 degrees. And then it's going to roll another 90 degrees, which is now 180 degrees. And then at the 3 second mark, it's at 270 degrees. And now it's at the 4 second mark, it's made one full revolution in those 4 seconds. So basically, it's rolled through 360 degrees. Okay? Well, if you put 360 degrees and convert 360 degrees to radians, what you would find is that if you convert 360 degrees to radians, you would find that is equal to 6.28 radians. Well, 6.28 radians is 2 pi. So it starts out at 0 degrees, which is also then 0 radians. And then here it's at 90 degrees, so it's rolled a little bit. Now it's at 90 degrees, which is actually pi over 2 radians. And then here it's at 180 degrees, which is actually pi radians, so that would say 3.14 radians. And then over here at 270 degrees, that would be, what is that? 3 pi over 2, so 1.5 pi's. And then finally, when it gets back up to the top here, it's rolled through 360 degrees at the 4 second mark, and that's actually 2 pi. So in a way, radians is a conversion of degrees to pi's. And the reason why we think about rotation in terms of radians is that's a really easy way to convert to linear motion. Okay? So let's talk about that. Well, how far does this wheel roll? Okay? Well, these dots here are at the circumference of the circle. Okay? So from here to here, let's say this wheel would roll in from 0 seconds to 1 second. Let's say 0 seconds is right here. So let's say the wheel, the center of the wheel would be right here at the 0 second mark. Okay, 0 second mark. And then it's going to roll a bit. I'm going to try to keep this, even though I made a smaller wheel, I'm going to try to keep this length, that length. And now, it's now at the 1 second mark. The dot's at the 1 second mark right here. So now it's rolled 1/4 of its circumference, right? A little bit further down the road here, from this length from here to here, you know, if you actually walked this length, that would be this length from here to here. Well, now that dot is going to be here at the bottom, at the 2 second mark. Okay, and so now at the 2 second mark, it's rolled half its circumference. A little bit later on, it's at the 3 second mark, and that dot is now right here. And now it's rolled 3/4 of its circumference. And then finally, that dot is at the top again. 3 seconds, and then 4 seconds. So now it's rolled 1 full circumference in that period of time. So how far it rolls in the x direction, and it's rolling in its displacement is going to be in the positive x direction, is actually going to be 2 pi times r. Or in our case, 2 pi times 1 meter, which is actually going to be 6.28 meters, which is actually the circumference of the circle. And that's also why 2 pi is in here for radians. In other words, you could actually just say delta x is actually going to be the number of radians. So we could actually say this. It's the number of revolutions, so the number of revolutions times 2 pi r. And that's actually a better way of writing its displacement in the x direction. It's going to be the number of turns this wheel makes, 1, 2, 3 turns, a half turn, a quarter turn, a tenth of a turn, times the circumference of that circle. Okay? And this is a way to convert linear motion and also tangential motion, by the way. The distance this is rolling right here, this circumference, this part of the circumference is this distance from here to here, okay, in that 1 second, okay. So that would be a quarter turn, so 1/4 times 2 pi times 1 meter, so that would be pi over 2 times 1 meter. So that would be something like 1.28 meters, is that how far that would have rolled. So this is a good way of taking how many degrees or radians or revolutions something has spun through, some wheel is turned through, into how far this wheel would have rolled, or it's how far this dot would have turned in a full circle, right? So if this wheel wasn't actually rolling, it was just like a record player spinning in place, this dot would be moving to the right. It would have a tangential velocity vector, which incidentally is the same thing as the center of the wheel velocity vector. And then now that dot is moving down here, and over here it's moving to the left, over here it's moving up, and over here, and then now at the 4th second it's moved to the right. So that's also the distance it's rolling tangentially, not just the wheel itself rolling across. They're the same thing, actually. All right? So here's what I would like to propose. Instead of keeping things in terms of degrees or radians, just keep it simple. How many turns did that wheel make? How many numbers of revolutions did that wheel actually roll? Did it turn twice, 3 times? Did the wheel only roll a quarter of a revolution? Okay? As long as you keep it simple, you don't have to memorize too many formulas, because the number of revolutions times 2 pi r is how far something would have rolled in the x direction or in the y direction, or what its tangential displacement would have been as well, right? And then if they need the answer in terms of radians, you could just take the number of revolutions multiplied by 2 pi, and that's the number of radians it is. And if you need the answer in terms of degrees, once you've done all the math and everything that we're about to do in the next chapter, in the next part of this, you can convert it from revolutions to degrees. So try to keep it simple here. So in this particular case, to see how far something rolled, all you have to do is go, well, it's got this number of revolutions, this number of times the wheel is spun, times the circumference of that circle, and that's how far the thing would have rolled across the floor. Okay? So pretty easy. So everybody knows the formula, well, most everybody knows the formula for circumference, and as long as you just realize that it's a number of times that wheel has spun, and that's going to be the circumference, it's really very little memorization. Okay. So, for example, if a wheel is turned 1.5 revolutions, and you want to know how far it went, you don't maybe you don't do this and convert it to radians. Maybe just say it's turned 1.5 revolutions and multiply it by 2 pi r. And in this particular case, r is going to be our 1 meter radius wheel. That's going to be 9.42 meters. And if they want to know the number of revolutions it's gone through, well, the number of radians it's turned through, well, then you just go, this is 1.5 turns, so that's going to be 2 pi plus a half of a 2 pi, which is just pi, so that's 3 pi right there. And then 1.5 times 360 degrees is 540 degrees. So it's a real easy and simple way to look at motion if you keep it simple. Just the number of revolutions times 2 pi r. Okay, and if you need to convert to radians, it's just the number of revolutions times 2 pi, or it's the number of revolutions times 360 degrees. Okay. All right, let's talk about the relationship between tangential speed and tangential/linear speed, and also angular speed or angular velocity. All right, so here we go. We've got our 1 meter wheel, and this time it's going to make one full revolution in 10 seconds. Okay, so I'm going to mark out a motion diagram on this. Okay, so it starts here at the top at 0 seconds. For some reason, I always want things to start at the top. And then at the 1 second mark, it's here. 2 second mark, it's here. 3 second mark, it's here. So I'm going to try to keep this rolling at a constant speed. There's no acceleration. It's not speeding up or slowing down. 4 seconds mark, it's here. 5 seconds mark, it's here. 6 seconds mark, it's here. 7 seconds mark, it's here. 8 seconds mark, it's here. 9 seconds mark, it's up here. And then 10 seconds, it's back to the top to where it was. Okay, so this thing is rolling one full revolution over the period of 10 seconds. Okay, and we want to know what is the angular velocity of this. Okay, we also want to know what its linear velocity is, and finally, is there a way to relate the equations for linear velocity to angular velocity? All right, so pause the video and try to answer these 3 questions on your own. Okay, pause now. All right, we're back. So angular velocity wise, so this is called omega. All right. Omega is the representation for angular speed or angular velocity. Okay. And essentially, that is the number of revolutions. Since we're keeping things in terms of revolutions, it'd be the number of revolutions over the total time, difference in time of when it started to when it stopped. It's also the number of radians it rolled through that period of time, or the number of degrees it rolled through. So basically, it's the angular displacement that we've been studying on the last one, which was right up here, the angular displacement, which is similar to angular to linear distance. So it's angular displacement over the period of time. And we're going to keep things in terms of revolutions. So I'm going to subscript this, the number of revolutions. So it made one revolution over that 10 seconds, which is 10 seconds minus 0 seconds. So this is just one revolution per 10 seconds, which is 0.10 revolutions per second. Okay, so as long as we keep it simple, you don't have to do any conversions. And then if you wanted this in terms of radians, you would just multiply the number, you would multiply this by 2 pi. So that would work out to be 0.628 radians per second. Oops, radians per second. Or it'd be the number of degrees per second. So the number of revolutions would be 360 degrees over 10 seconds. So this would be 36 degrees per second. Okay? So you could write it a bunch of different ways. Okay? Well, let's use this to find the linear velocity, right? So linear velocity is just the velocity that it's rolled through. And linear velocity in its basic definition is the linear displacement over the period of time. Well, in doing this, from the last problem, we found out that it rolled 6.28 meters. One full revolution of a 1 meter wheel is going to be 2 pi r. So it rolled the number of revolutions, theta revolutions, times 2 pi r, which is our linear distance, over delta t, right? And this is going to work out to be 6.28. Actually, it's 6.28 meters over 10 seconds, right? 10 seconds minus 0 seconds is delta t. And that's in the positive direction because it's rolling to the right. The wheel's rolling to the right. So this is going to work out to be 0.628 meters per second. Okay? There's another way to write this, okay, where we link velocity here, this velocity to angular velocity, okay? So another way of writing it is this. To find out how far something is rolled, wouldn't it be better just to take the angular speed in revolutions, okay? And so this is the angular speed in revolutions. This is the angular speed in radians. And this is the angular speed in terms of degrees, right? Well, wouldn't it be easier just to take the angular speed in revolutions and then multiply it by the circumference of the circle? Well, if we do that, then that's going to be 0.10 revolutions per second times 2 pi times 1 meter, 2 pi times 1 meter, which is 6.28, right? So this is 6.28 meters times 0.1, right? Which is going to work out to be 0.628 meters per second, right? Revolutions is unitless, and so is radians and degrees. So it's just 1 meter divided by 1 second. It's not 1 meter revolutions times a second. So this is a really quick, easy way to relate linear velocity or tangential velocity. In other words, tangential velocity is or tangential speed, in other words. This is the velocity vector in this direction. Over here, it's the velocity vector. It's the same velocity vector down. It's the same velocity vector to the right. It's the same velocity vector up. Incidentally, the size of that velocity vector, if this wheel is rolling to the right, is the same size as the center of the wheel's velocity vector to the right. So this size and this size, they're the same thing. So the top of the wheel's velocity vector on the tangential velocity vector is the same thing as the entire wheel's velocity vector to the right. Or in other words, the center of mass moving to the right. Okay? So this is a real cool way to relate angular velocity to linear velocity, it's just really all you're doing is multiplying it by 2 pi r. Kind of in the same way that we related angular displacement to, linear displacement to angular displacement, right? It's the same thing, okay? We'll find out later on that actually acceleration takes on the same thing too. The number of turns or number of revolutions something is made, or actually the angular acceleration in revolutions times 2 pi r as well. So that's supposed to be an alpha. That's terribly written. Sorry. So I'll just write a little alpha there. Okay. So there's this pattern here. Relationship between angular displacement and linear displacement is just multiplying it by 2 pi r. The relationship between angular velocity and linear velocity is just multiplying angular velocity by 2 pi r. Well, multiplying angular acceleration by 2 pi r, you get the linear acceleration. So that's why this is really powerful, just keeping it in terms of revolutions. Okay. All right. Well, that basically gets us up to this. If you wanted to have it in terms of rads, incidentally, your books have this. They'll often write R omega. They won't tell you that omega is the radial. It's the Radians interpretation of omega, right? Which this is going to be then R times 2 pi times omega revolutions, right? So that interpretation right here of rads, omega rad, is actually 2 pi times omega revolution, okay? So you'll see that often in your book. So whenever you see an omega times r, that's actually 2 pi times the number of revolutions per second it made in a period of time. Or you could say the number of radians per second times r. The 2 pi is built into that interpretation. Okay. Well, let's talk about something else. So since we have wheels that can roll, so we have linear interpretations of wheels that are rolling, where if something is rolling in the x direction, and here let's say it's the 0 mark is right here, and it's rolling to the right, it's rolling in the positive x direction, and to the left is negative x direction. Conversely, if something is moving up or down like a yo-yo on a string, and it's unspooling itself, if it's spooling itself in the upwards, that would be the positive y direction, and downwards is negative y direction. Well, there has to be a relationship, since we're talking about angular velocity, that's angular speed plus it has to have a direction to it, like a positive or negative, just like in the linear interpretation. Well, what physicists have done is they use this thing called the right-hand rule. And so this right hand, basically what you do is that if you have a wheel spinning in this way, it's spinning counterclockwise. So this wheel is going to be spinning in this direction. You know, so this is counterclockwise. CCW is often written that a wheel is spinning counterclockwise. Well, if this wheel was spinning counterclockwise and you grabbed it, your hand would kind of lurch, your fingers would lurch in the direction. Your thumb would be pointing upwards or out of the page. That is considered positive Z. Positive Z is the third dimension of this. Up and down is the y direction. Left and right is the x direction. Out is negative z. Out is positive z, rather. Sorry about that. And in is negative z. Okay. Let me try a different color for that so it shows up. So if something is rolling clockwise, and this is going to be clockwise, it's rolling in this direction around this way, well, that's rolling into the page, and that would be considered negative z. Essentially, what you can say is this, that counterclockwise is considered positive z, and clockwise is considered negative z, okay? Which is kind of weird, because if you have a wheel, let's say we have a wheel and it's rotating to the right, it's rotating clockwise, this is a wheel rotating clockwise, which direction would that go? Well, it would have a positive x direction velocity vector. However, this omega is in the negative direction because of the right-hand rule interpretation. So if this wheel is rolling clockwise across the ground, it would be rolling to the right, so it would have a positive velocity vector in the x direction, but a negative omega, because the right-hand rule is saying it's rolling clockwise, which is in the negative z direction. Okay, I don't like that, but that's essentially how all of our textbooks are written. Okay, so that is the right-hand rule, and that's how to decide if something has a positive or negative velocity vector or acceleration vector in angular terms. Counterclockwise is positive z, clockwise is negative z. All right? All right, well, let's move on. This is one of my favorite comic strips, Calvin and Hobbes. So if you ever had a chance, maybe pause the video so you could read this. But this is where his dad wants to show his son something interesting, and he's basically saying you've got 2 points on a record table right here. Oops. So he's saying you got 2 points on a record table. You have one, here's the center. You have a point 1 right here and a point 2 on the very outside. The point on the outside is going to make one full, they're both going to be right next to each other the entire time this thing is spinning, right? 1 is here, 2 is there. Over here, at a quarter turn later, it's going to be here. 1 is going to be next to 2 when it's on the half turn. 3/4 of a turn is going to be here, and then it's going to return. So the entire time this thing's spinning, 1 is going to be right next to 2. Point 1 is going to be right next to point 2. However, it's kind of weird in the fact that point 2 is on the outside of the wheel, while point 1 is on the inside of the wheel, or the half revolution. So point 2 is going to actually turn 2 pi r, where r is the radius, well, and that's going to be how far it's spun in the x direction, how far it's spun rotationally. Well, point 2 is rotating, it's got a half radius at r/2, which basically is actually just pi times r, which is how far it's spun for point 2, which means in order for point 1 to be right next to point 2 the entire time, point 2 has to be actually moving twice the distance. Then point 1 has to be moving, oh boy, this should have been point 2 and this should have been point 1. So this point 2 has to be spinning a full radius and has to be moving further. In fact, point 1 is only moving half the distance of point 2. So, but yet they're right next to each other the entire time, and it's kind of odd. So I just maybe just pause this and read it. It's really cute and fun. Anywho, moving on. Well, this is that exact problem. Bonnie sits here on the outer edge, and Clyde sits midway in between Bonnie and Clyde. So the merry-go-round is going to make one complete revolution every 2 seconds. Compare Clyde's angular velocity to Bonnie's. So will Clyde's angular velocity be the same as Bonnie's? Will it be greater than Bonnie's? Or will it be less than Bonnie's? So pause the video and think about what you think. Think about what's going on, right? And I'm talking about angular velocity. Pause now. All right. Well, if you think about it, angular velocity, from what we've said before, is the number of revolutions per second. So it's the number of revolutions that something is made over a period of time. And so Clyde is doing one full revolution clockwise. So he's making one full clockwise revolution in 2 seconds. So basically he's spinning at a rate of a half revolution per second. And this is for Clyde. Well, Bonnie is on the outside, and Bonnie is also spinning at a half revolution, one revolution every 2 seconds as well. Okay. So basically what this is saying is this. So even though Bonnie is on the outside and Clyde is at half the radius of Bonnie, they actually are turning the same amount every second. They're doing one full revolution every 2 seconds, or a half revolution per second. So the answer to this is Clyde's angular velocity is the same as Bonnie's. The linear velocity is going to be different, okay? Because the linear velocity, from what we've in our new equation, linear velocity, or tangential, in this case, since the wheel isn't rolling across the floor, these guys have tangential velocities. So again, if this wheel is rotating counterclockwise, is rotating clockwise, then Clyde would have a velocity vector in this direction at this point. That's Clyde's velocity vector, v sub k. Bonnie's velocity vector is going to be twice that of Clyde's. Okay, and that is because Clyde is at a half radius of Bonnie. So let's do it this way. So from the last one that we learned, both Bonnie and Clyde have the same number of revolutions per second, but they're at different locations. Clyde is at, and this is K for Clyde. Clyde is at a radius of R over 2. So basically, they're both making a half revolution from the last problem per second. And let's say this is a 1 meter wheel, just to keep things easier. So basically, Clyde is moving at 2 pi times 1 meter divided by 2, or a half meter, which is then going to be, this is going to be 3.14 meters. So Clyde is going to be moving at half of 3.14. So 3.14 divided by 2 equals 1.57. Okay, so basically, this is going to be a half revolution per second times 3.14 meters, which is 1.57 meters per second. And so that is Clyde's velocity. Bonnie's velocity is going to be a little bit different. she's moving at the same angular velocity, a half revolution per second, or one full revolution every 2 seconds. It's the same thing, but she's at the full radius, which is 1 meter. So this is going to be a half revolution per second times 6.28 meters. So in other words, Bonnie's velocity vector is going to be 3.14 meters per second, and Clyde's is going to be half of hers. So Bonnie, in order for Bonnie to stay right next to Clyde, she's got to be moving with twice the speed of Clyde at every point on the circle. I know it seems weird, but that's the relationship between polar and linear. Okay. So in this problem, who's got a larger tangential velocity? Bonnie does. Let me just circle out again. Bonnie. There we go. All right. So here's that explanation right here. These two bugs, it's the same problem. This bug is moving twice as fast as the center bug, the bug at the half radius. Okay. Well, now we have a really cool relationship between angular velocity and angular displacement, and linear velocity and linear displacement. Okay. Well, similarly, there is an angular acceleration. Objects can speed up and slow down while they're turning. So let's attend to that. Okay. Incidentally, I'm going to write some stuff over here. So from this last page, where there's an x direction is now a theta. Where there's a v, there's going to be an omega. And where there's an a, there's going to be an alpha. Okay? So the relationship of linear displacement to angular displacement, we're going to use revolutions as our basis for this. Number of revolutions times 2 pi r. For linear velocity, it's going to be angular velocity in terms of revolutions times 2 pi r. And for linear acceleration, it's going to be angular acceleration times 2 pi r. So again, the equations of motion for linear velocity is the same equations of motion for angular velocity. You're just going to be multiplying all the angular velocity and angular displacement and angular acceleration by 2 pi r to become linear velocities, accelerations, and stuff. So they're the same equations. They really are the same motion. Just one is turning in a circle, the other one is linear interpretation, and the relationship between these two is through the circumference of the circle. Okay. But let's start building equations based on what we know. So, for example, you have a wheel right here that is speeding up. They said it's speeding up counterclockwise. Okay, so you have this wheel right here that is rolling counterclockwise. So so using the right hand rule, you should be pointing your thumb at your own face, and your hand should be making a curl. And we said that is going to be the positive z direction. Since your thumb is pointing out of the page, if this wheel was spinning counterclockwise and you grab this part of the wheel, your fingers would lurch to the left. Your thumb would be pointing out of the page at your own face. Okay? Well, if this wheel is then spinning counterclockwise, the center of mass of the wheel would be rolling to the left in the x direction. So it would have a negative velocity vector in the x direction. Okay? Well, if we're speeding up in the negative x direction, okay, the definition of speed up is that your velocity vectors and acceleration vectors are in the same direction. So that means if we're moving to the left and we're speeding up, that means your acceleration vector is also going to be to the left as well. Okay, that's the definition of speed up. Well, the same thing goes for the angular interpretation of that. If we've got a positive omega and it's speeding up, that means our alpha has to also be positive or counterclockwise. Okay. Incidentally, the top of the wheel will have a tangential velocity vector that is the same size as this. So its tangent v sub t, or tangential velocity vector, is going to be the same size as the entire wheel's velocity vector. Just the top of the wheel is going to be to the left. If this dot was here and the wheel was rolling counterclockwise, it would then be pointing down. And over here, it would be, this dot would be moving to the left. And it's again the same speed as the entire wheel, because it's at the circumference. And this velocity would then be going up. So that's just how that's relationship of tangential velocity vector to the overall velocity of the wheel itself. They're actually the same thing as long as this dot is at the circumference. Okay. All right, let's try another one. That was a lot of information. Oh, incidentally, so we're talking about the x direction, the velocity vector is going to be to the left, and so is the acceleration vector. So this velocity vector, so those velocity vectors and acceleration vectors will all be negative, okay, for the linear interpretation. The angular interpretation, they're all going to be positive, right? So this is going to be positive, those are going to be positive, positive omega, and the acceleration is going to be positive, okay? So by interpreting this, we're actually adjusting these equations to our specific case. All right, let's go through the next situation. You have a wheel who's rolling counterclockwise. So that means he's going to have a positive, it's going to be a positive omega, and it's slowing down. Okay, well, from our earlier class, again, this is going to have, it's moving counterclockwise, so the wheel itself is going to be rolling to the left, and that means the tangential velocity at the top is going to be to the left as well. The same amount as this one. Well, and then it'll be down. Anyways, the same interpretation here. However, it is slowing down. What that means is this wheel, its initial velocity vector is going to get smaller over time. And I should have done that here as well. So let me fix something real quick. These velocity vectors, if it was speeding up, it would start that, and then it would get a little bit longer, and then a little bit longer, and then a little bit longer, according to that acceleration vector. Okay. Incidentally, look, going back to this wheel is rotating counterclockwise, but it's slowing down. That means the center of the wheel is going to be, the center of the mass of the wheel is going to have a negative x direction velocity vector. But the definition of slowing down means the velocity vector is opposite the direction of the acceleration vector. So that means the acceleration vector is going to be pointed in the positive x direction. Okay? Similarly, since the velocity vector and acceleration vector is in opposite directions, positive omega is going to have then have a negative alpha, or negative angular acceleration. They have to be in opposite directions for the center of wheel to slow down as it's moving to the right. Well, we're making equations again. This velocity vector is negative, this is negative, this is negative. The acceleration is positive. This velocity vector, so the linear velocity vectors are all negative. The linear acceleration vectors are all positive. But the omegas over here are positive. But the acceleration vectors in the angular interpretation are all negative. Okay? So we're adjusting our equations. Again, we're adjusting our linear equations and angular equations to fit this particular case. Finish this up, and we'll start doing some problems in a moment. Okay? Okay, so now, in this case, let's do this one first. Let's say we're speeding up in the clockwise direction. Well, that's going to be a negative omega, which means this wheel is going to be rotating, is going to be moving to the right. So in the positive x direction, the wheel is going to be moving to the right, but we're going to have a negative omega. And we're speeding up, means our linear velocity vector and our linear velocity vector and linear acceleration vectors are both going to be in the same directions, which then means our angular acceleration vector is going to be in the same direction as our angular velocity vector, which means these are all positive in the linear sense, but these numbers are all negative. Okay. So that's the relationship between linear velocity and angular velocity for a wheel speeding up clockwise if it's rolling to the right. Okay. Let's do the very last problem, which means this. It's slowing down while moving clockwise, so negative omega, positive velocity in the x direction. But slowing down means its acceleration vector is directed opposite the velocity vectors, which means alpha is going to be positive. So this is going to be a negative alpha. Oh no, it'll be a positive alpha because omega is negative. Positive velocity vector, negative acceleration vector. Okay, which means these linear acceleration vectors are going to be negative, but the velocity vectors are going to be positive. And in the angular sense, omega is going to be negative, but the accelerations are going to be positive. Okay? So this is how you change angular velocity and angular acceleration to linear velocity and linear acceleration. This is how you interpret the differences between those two things. Okay? So there are two tutorials related to this. Okay? There's page 7.5 tutorial and page 7.6 tutorial. So I would like you to try those out and see how you do on them. Okay. We're going to go ahead and break for today, but use what you learned to interpret. This is about interpreting linear velocity and angular velocity. Okay. So notice this is a larger circumference here. This is a smaller circumference, and this is the most smallest circumference. So you're going to interpret how far something moves in the linear direction and related to how the number of turns it makes per second. So this is the linear velocity stuff, This is the angular velocity stuff. In page 7.6, you're going to be doing what we did before back in motion in chapter 1, but you're going to be doing translational motion related to angular motion. Okay, so for example, let's do this first one right here. The ball is rolling down the first slope, so the ball is going to be rolling to the right. So it's going to be rolling down this slope, which means it's rolling in the x direction, but it's also moving in the negative y direction. Okay, and it's going to be speeding up too. So it's got a positive x direction velocity, but a negative y direction velocity. It'll be speeding up as well. So in the x direction acceleration, it's going to be the same direction as the x direction velocity. And in the y direction, it's going to be in the same direction as the y direction velocity vector. Okay? But for this wheel to roll to the right, it's got to roll this direction, which is clockwise, which means it's got a negative omega. And since it's speeding up, its omega and alpha have to be in the same direction. So that's kind of how you approach page 7.6. Okay? So thank you very much for listening to this, and I hope to see you again and talk to you again in the next video. Bye.